Hello, and welcome back to Physics in Minutes. Today, I'm going to explain free body diagrams and forces. How do you draw a free body diagram, and what is a force anyway? That's what we're going to go over in this video, so stay tuned. Before we get to free body diagrams though, let's look at what force is anyway. Force has the very well-known equation F equals ma, which stands for force equals mass times acceleration. And let's look at one brief example. Suppose we have this guy with a mass of 10 kilograms. And let's try to find the force due to gravity on this guy. So the force, F, is just mass, which is 10 kilograms, times the acceleration due to gravity, which hopefully by this point you recognize that to just be 9.8. If you multiply those together, you end up with force equals 98. Now we have to plug in the units, and this is really important. We have kilograms from the mass, but we also have meters per second squared from acceleration. When you put all of that together, thankfully, it has a new unit, and that unit is just N for Newton. So whenever you're dealing with a force, the unit of force is a Newton. And here we have simply that the force is just mass times gravity, and that's what the force of gravity is always going to be. And I want to highlight real quick that the force we just calculated is equivalent to the weight. Mass and weight are not the same thing. Sometimes we think it is, but weight is just the force due to gravity. But now let's look at free body diagrams. We have a hand that is pushing two blocks, block A and block B. A has a mass of 2 kilograms, B has a mass of 1 kilogram, and they are right next to each other. So if you push A, you're obviously pushing B. We're going to try and use a free body diagram. And the point of free body diagrams is that it can help you determine the net force on an object. When I say net force, you will sometimes see this written like that. And that just means you add up all of the forces and find out what the net force is. You generally do that in the x direction and then do it again in the y direction. And as we just saw, since force is mass times acceleration, if your acceleration is 0, then that means the entirety of your force has to be 0. So if the acceleration of any object is 0, then the force in both the x and the y direction have to also be 0. That's a really nice thing that we need to recognize because it comes up a lot. So now let's draw the free body diagram for these blocks. Let's start with block A. So one thing you can do is you draw a little circle around your block and try and find the forces that are going through that circle. For example, if we look at the hand, we obviously see that the hand is pushing the block to the right. So we'll draw a little arrow going to the right and we'll call that force of H for force of the hand. We also have, if we have friction, that's going to be pushing the block back to the left because friction always opposes the movement. So we'll just say that's F for force of friction. Now, because this block is on Earth, it obviously has some force due to gravity, and that is going to be pulling it down like this. We'll call that the force of gravity, so Fg. Now, there is an opposing force to gravity, and we know that because the block is not falling through the ground, something is stopping it from moving down. That is generally called the normal force. So we'll call that Fn for F normal. There's one more force here that we haven't looked at, and that is the force of block B on block A, because B is also trying to stop A from moving. So there's one more force pushing A to the left, and it's getting a little bit cramped now, but that is going to be force of B on A, so FBA. So we have done the free body diagram for A, we now have to do the same thing for B. And to make this a little bit nicer, I'm going to shift it slightly so it's not on center with block B. So automatically we know the force of gravity is also pointing down, and there's once again a normal force. Those are going to be different from the force of gravity on A, but we'll just leave it like this for now. There is also a friction force, which is pushing B back, but now there's a force pushing it forward, and that is the force of brick A on B. So we'll just call that FAB. And that is a free body diagram. I apologize if it's a little bit hard to see here, but the basic idea is you look at your object and you determine what forces are acting on that object directly. There's one thing that I want to point out, and this is a very common problem. You see that on block B, we do not have the force of the hand anywhere. And that is because the hand is not touching block B. The hand is pushing block B indirectly through block A, but the hand itself you can kind of consider irrelevant when you're drawing the free body diagram of block B. And that's really important. Do not include the hand because it's not directly touching block B. So now let's throw in some numbers and see what we can do from here. The friction on block A is going to be 10 newtons, and the friction on block B is 5 newtons. And it makes sense that the frictions will be different because block B has less mass. And we'll find out soon that friction is related to mass. They're moving at a constant speed of 1 meter per second. So now the question is, what is the magnitude of all of the forces we drew in the free body diagram? And then also, what's the net magnitude of force? Let's try and find that. So first, let's write out the things that we know. We know the masses, we know the friction, and we know the velocity. So we're going to start off looking at both blocks in the y direction first because that's a little bit easier. So remember, this symbol here just means the net force. So we'll do the net force in the y direction for block A, and then the net force in the y direction for block B. And they're going to be similar, just a little bit different. Based on our free body diagram, there were only two forces in the y direction. Do you remember what they were? They were the force of gravity and the normal force. And since gravity is pulling it down, we're going to give that a negative sign. The force of gravity is a negative, which means that by consequence, the normal force must be positive because it's pushing it back up. So now we're going to start plugging in numbers. We don't have the normal force, so we can't plug that in, but let's just keep going. The force of gravity, remember, is just mass times gravity. If we're looking at block A, the mass is 2. So 2 times 9.8 gives us 19.6. And that's in newtons. And now we add the normal force, which we don't have. However, there is one thing that we haven't pointed out here. What do you think the net force in the y direction is on this block? Keep in mind, the block is not moving up and down in the y direction. It's not jumping off the table, which means that there can't be any movement in the y direction. And if there's no movement, the acceleration in the y direction is just 0. So what that means is the net force, Fy, has to equal 0 as well. So that means that the normal force is equal to the gravitational force, just in a different direction, which makes sense. If gravity is trying to pull something down, the table is going to push it up at the exact same force. If it were more force or less force, it would either jump off the table or go through the table, and neither of those things are happening. So the normal force is 19.6. The gravitational force is minus 19.6. This is for block A. We can do the same thing for block B and just change up the numbers. The only difference is the mass is 1 instead, and so if we do that, we end up with 9.8 newtons is the gravitational force with a negative, and then the normal force is just a positive. So we have done the net force in the y direction here. And one of the reasons why a free body diagram is important is because it helps you think about what all the forces are before you start plugging in the numbers. So now let's try to find the net force in the x direction. Well, we'll start with block B because it's a little bit easier. So in block B, the only forces we have are the force of A on B, and that's just because the block A is pushing B to the right, but we also have the friction force. Since the friction force is pushing it to the left, we'll call that a negative number. And then the force of A on B is a positive number. We have both of these, but again, we don't know what the force of A on B is. But that's okay, because there was one other piece of information we haven't yet used. And that is, right here, the velocity. It has a velocity of 1 meter per second. If it has a constant velocity, what does that mean about acceleration? Since acceleration is the change of velocity, if velocity doesn't change, acceleration must be 0. And by consequence, that means that the net force in the x direction has to be 0 as well. So kind of like we just did, that tells us that if the net force is 0, then the force of A on B minus the friction force, which in this case is 5 newtons, has to equal 0. And so the force of A on B is just going to be 5. Fairly simple. So block B wasn't all that hard. Let's remember this, that the force of A on B is 5, because it'll come up when we're looking at block A. So now let's do that. The setup is all going to be the same. The net force in the x direction is going to be the force of the hand now, moving to the right, minus the force of friction, moving to the left, minus the force of B on A, also moving to the left. Now here, you have to recognize something about the force of B on A, and that is that it is a Newton law pair with the force A on B. What that means is that they are the same force. They're in different directions, but it's the same number, which kind of makes sense. If A is pushing on B, B is pushing back on A with that same exact force, which means that we have that number as 5 newtons. So let's plug everything in, and once again, since there's no acceleration, the net force has to be 0. That gives us the force of the hand minus the friction force, which in this case is 10, minus the 5 newtons from force of B on A, which tells us that the force of the hand has to equal 15 newtons. And it makes sense that that is going to be the highest force, because this hand has to exactly balance and counter the friction forces of both block A and block B, which when combined give you 15 newtons. And that is it for my explanation of free body diagrams and the introduction to forces. I'm sure I'll go into a bit more detail on what a force is a little bit later and how to solve more complicated problems, but that's it for this video. If you have any questions or comments, go ahead and let me know down in the comment section below. And if you appreciate this content, please leave a like and subscribe. I really appreciate it. Thank you for watching, and come back next time. I'll see you then.